Hello, Hornets, and thank you for joining me today. Today, we're going to be talking about the fundamental identities. Now, the fundamental identities as we have them are in our textbook, and I'm just going to go ahead and take a look at those fundamental identities with you right now. They are in the blue section that we have right here. Now, you'll notice that each of them have names, and all of them we have worked with in some fashion or another. For example, we know that the reciprocal of the sine is the cosecant. The reciprocal of the cosine is the cosecant. The reciprocal of the tangent is the cotangent, and vice versa. So if we take the reciprocal of cosecant, we get sine. The reciprocal of secant is cosine, 1 over cosine, and cotangent is 1 over tangent. So it's important to keep in mind that we have worked with these, we've seen them, and your job now is to remember them. So you have to learn these formulas, these identities, so that we can then validate, verify, and find new identities that are going to be more helpful. This will then allow us to move forward in this chapter as we both solve as well as work with things like the half angle identities, the double angle identities, the sum difference identities, and the product sum identities. These are the identities that we have to work on and learn and know how to use by the end of this chapter. So let's just take a look at some more. Tangent, which we know is the opposite over the adjacent, where the opposite side of the right triangle within our unit circle is sine of u, and the adjacent is cosine of u. That means that the tangent of u is the sine of u divided by the cosine of u. Notice that the cotangent, being the reciprocal of the tangent, means that instead of having sine over cosine, we have cosine over sine, which is representing the adjacent over the opposite. We then have our Pythagorean identities. And we have gone through when we were looking at our unit circle. And we said that having the tangent forms, or having a point on the unit circle, forms a sine and a cosine point, which we can then call sine squared plus cosine squared equals 1. Working with the outer edge of the tangent, or the unit circle, and forming a vertical tangent line, we end up getting the Pythagorean theorem 1 plus tangent squared u equals secant squared u. Working with our horizontal tangent to our unit circle, up hitting the point pi over 2, 0 pi over 2, we end up having another Pythagorean relationship, which is 1 plus the cotangent squared u equals the cosecant squared u. We have also seen that because the sine, the cosine, the cotangent, and the tangent, the secant and the cosecant are off by a phase shift, we can represent it in terms of degrees or radians as a cofunction, which means that we can convert a sine into a cosine or a cosine into a sine. In order for us to change a sine into a cosine, we are going to work with this one. So here's our cosine of u, and we do pi over 2 minus u in order to find the equivalent sine. Same thing if we have the sine of u. To find the cosine, we're going to do pi over 2 minus u. Tangent and cotangent are once again pairing together in the same pattern, and secant and cosecant are pairing together in the same pattern. We also saw, as we were working with our unit circle, that since we are moving counterclockwise, when we have the sign of the clockwise rotation, we end up getting the opposite of the sign at that value. So think about it going downward. We go down pi over 3, we're going to have the opposite of the sine of pi over 3. Cosine is an even function and therefore is not affected by that negative. As a result, we drop it, because whether we go down or up, going clockwise or counterclockwise on our unit circle, we are still moving along the x-axis in the same manner, from our right to left. Secant, being the reciprocal of the cosine, is also even. As a result, it has the same relationship. Notice that when I have a negative theta or a negative u value for a cosecant, just like with sine, we're going to pull out the negative. And it will be the opposite of the cosecant at that counterclockwise rotation. Once again, this is a reference angle that we are working with. Tangent is also odd. So is the cotangent identity. Now, please be aware when we are talking about our inverses, those are the arc sine, arc cosine, arc secant, arc cosecant, etc. We now have other issues because not all of the functions are going to have or are going to be even or odd. And as a result, they might be neither. Let's just take a quick look at one of those real quickly before we go back and we start verifying identities. And I want you to think of the arc cosine. The arc cosine starts here, goes through at pi over 2, and ends up here. So right here, we're looking at our axis is starting at 0 pi. This is a length of 1. This is at negative 1. Notice our domain is from negative 1 to 1. The range, 0 pi, pi over 2, going up to pi. Now you'll notice this is not an odd function. In order for it to be an odd function, this point right here would have to be represented through the origin over here. It is not. Notice that it is not an even function, because if it were an even function, we would have a reflection over here. But there is no reflection through this y-axis. So the function is neither even nor odd. Since the function is neither even nor odd, we have to say neither. Okay? So whenever you are asked, is the arc cosine even or odd, you would say neither. But take a look at the arc sine. The arc sine looks like this. Now you'll notice that if we were to use our geometry skill and reflect it through first our x-axis and then reflect it through the y-axis, you'll notice it overlaps. This is a classic example of an odd function. So we can also look at it and say this point here and this point here are reflected through the origin. That is also the characteristic of an odd function. Another odd function would be the arctangent. Let's just take a moment and look at our arctangent. The arctangent has two asymptotes. One asymptote at pi over 2, and one asymptote at negative pi over 2. These are horizontal asymptotes and are therefore limits. We know that our cotangent starts in the middle and is going to make a curve slowly bending toward its limit at infinity. Therefore, on the other side, it's going to do the exact same thing and approach its limit at negative infinity. Notice now, if we reflect and then reflect, we can see that it is indeed an odd function. If we look at a point, we can see that that point is reflected through the origin and once again holds the characteristic of an odd function. What I'd like you to do is think about the graphs of the secant and the cosecant now, and try to think to yourself, as well as the cotangent, are they even or odd, or are they neither? That's a question for you to think about, and the way you want to think about that is by looking at the graph of a secant cosecant. And you'll notice we have those graphs in our textbook. So if you were to look for them, let's just take a moment and find them so that we can see them. Here is our cosecant. Notice that if we were looking at the arc cosecant, this would have to be, this would have to be reflected. Notice that right here, as we are looking at this cosecant, this point right here and this point right here are indeed reflected through the origin. So we could say that the cosecant is also an odd function. Look at the secant. The secant, or the arcsecant, excuse me. So let's see, so here we have the cosecant and is an odd function, and we can clearly see that our secant is an even function. Let's now take a look at our arcs. So remember, when we're working with our inverse function, here is the arc sine. Once again, we can see that it is indeed odd. When we look at the arc cosine, we can clearly see that it is neither, once again being above. Excuse me as I try to get this into the right position. Here we see our arc tangent, and our arc tangent, once again, is odd. Now, when we start to look at the others, we will find that there are problems to it. And I seem to have lost my graph, which I so conveniently put off to the side so that I could show you the specific arc that I was trying to do. And of course, true to my normal state of being, I have simply lost it somewhere. So please, on your own, take a look at the arc cosecant and the arc secant, and take a look and see if they are even and odd, or neither. All right, we're going to go ahead and we're going to be taking a look at some identities at this point. So we're going to go to some problems, and we're going to see how we use our identities to prove things or to verify other formulas. Now, this is not a difficult process. The whole idea is we're going to have two sides of an equation. We have a left and a right. So if I were to say, prove that the cotangent, or verify that the cotangent x sine of x is equal to the cosine of x. In order to do this, we're going to have to work with our identity for our cotangent, and we know that the cotangent is equal to the cosine of x over the sine of x. We are going to do a direct substitution. We're going to leave the right side alone. Okay, now your idea here is to only work with one side. You cannot multiply both sides by a value. You cannot add or subtract on each side. You have to think about it as having a wall. These are two separate sides. So all I can do is change the left side. And in order to do that, I have to know my identities. If you do not know your identities, this is not going to be very much fun, and you're going to struggle with it quite a bit. So your first step is to learn those fundamental identities so that you can do the substitutions that I'm showing you. Notice, sine cancels, and cosine of x is equal to the cosine of x. We have verified the identity. Fantastic. Let's take a look at verifying another identity, shall we? Let's go ahead and verify that the cosecant of theta times the tangent of theta is going to equal the secant of theta. Now, the textbook, when you start working with these in your textbook, they're going to say, use your graphing calculator or your graphing utility to demonstrate and show that these are equal. That means they want you to plug this in under y1 and this under y2 and show that they overlap. For us, we're just going to change the right side so that the left side so that the left side will ultimately look at the right side. Look like it. So we're going to put secant theta there. And we're now going to think about, how can we change things or substitute them so that we end up with a secant of theta? Well, let's just take a look at what we've got. We know that the cosecant of theta is 1 over sine of theta. We also know that the tangent of theta is really the sine of theta over the cosine of theta. And we know that 1 over cosine of theta is equal to the secant of theta. So these are the three identities that we are going to be using in this problem. We start off by taking the cosecant of theta, and we're going to put in 1 over the sine of theta. I'm then going to replace the tangent of theta with sine of theta over cosine of theta, where the sine of thetas will cancel. I am then left with 1 over the cosine of theta. I want to show that it equals the secant of theta, and since I already know that 1 over cosine of theta is the secant of theta, I can go directly to my answer. Now you'll notice right now, I'm currently doing very, very simple verifications. The further we go through this chapter, the more difficult they will become. Now, be aware there are other formulas and other definitions that we have to use as well. For example, as you work in your textbook, you are going to encounter problems that are asking you to try to simplify, such as take the square root of 25 minus x squared, where x is really 5 sine of theta. And our goal is to try to figure out what does this simplify into. Well, we're going to take the x and we're going to replace it. Square root 25 minus x, the quantity squared. And inside of that parenthesis, we are going to put 5 sine theta. We're now going to distribute the square. We get 25 minus 25 sine squared theta. We're then going to factor out the 25 from this binomial, leaving us with 1 minus sine squared theta. That means that I can now distribute the square root into the 25 and the square root of 1 minus sine squared theta. This is going to give me a 5. Now I need to look at this one. We have the Pythagorean identity that says that cosine squared theta plus sine squared theta has to equal 1. That means that cosine squared theta has to equal 1 minus sine squared theta. Notice, within this one identity, there are a total of 3 of them. We also could have sine squared theta is equal to 1 minus cosine squared theta. So each of those 3 Pythagorean identities that we saw at the beginning in the blue that I was showing you a moment ago, which I'm going to show you again, have 3 corresponding identities associated. The one shown and the manipulation of the identity into 2 additional ones. For example, cotangent squared u is equal to cosecant squared u minus 1. We have 1 is equal to the cosecant squared u minus the cotangent squared u. Likewise, tangent squared u is secant squared u minus 1, and 1 is equal to secant squared u minus tangent squared u. Since sine squared plus cosine squared equals 1, sine squared will then equal 1 minus cosine squared, and cosine squared is 1 minus sine squared. Let's continue. That means that right here inside of this square root, I'm going to put cosine squared. Now, this brings us to one of our most important definitions that we have to remember. The square root of something, whatever it might be, the quantity squared. This is, by definition, an absolute value. And so when I put this in and I take the square root, I get 5 cosine theta. And it is an absolute value. Now, although the textbook may not ask you to put that absolute value in, I demand it. You have to see it because there is a difference between 5 cosine theta with an absolute value and 5 cosine theta by itself, because this could be positive or negative. But this can only result in a positive answer. The cosine may come out with a negative, but the absolute value changes it into a positive. And as a result, these two are not equal, and in fact have distinctly different domains. Cosine of theta is the domain from 0 pi to 2 pi. But this will only equal this when we have a specific narrowed or restricted domain for the first and the fourth quadrant. In the first quadrant, 0 pi theta goes to or equal to pi over 2, or 3 pi over 2, which is a 0, is less than or equal to theta, is less than or equal to 2 pi. This is now the domain where these two will be equal. And only if I restrict the domain can I say that they are. If I do not restrict the domain, they are not equal. Okay, that's critical, and you have to remember that. Alrighty. Let's take a look at another situation that you might be encountering as you're working with your textbook work. Oftentimes, they will ask you to find the solutions, and they want you to now find the solutions for sine of theta is equal to 1 minus cosine squared theta. Now, as we just saw, sine squared theta is 1 minus cosine squared theta, so we can do a substitution. Sine of theta is equal to the square root of the sine squared of theta. This is now giving us sine of theta is equal to the absolute value of the sine of theta, once again by the square root of something squared, by definition, is an absolute value. So the question becomes, when will these be equal? When they are equal, that is a solution. So let's take a look. In our unit circle, sine is positive in the first and the second quadrant. So as long as we have a theta that is in the first and the second quadrant, or from 0 pi all the way to pi, I will get an equivalent answer. So my solution is theta is an element of the real number set such that 0 pi is less than or equal to theta, which is less than or equal to pi. This is now representing all of my solutions on the interval given. Now, keep in mind that if I have an answer that is here, I can find all of my solutions by adding 360 degrees, or 2 pi k. So we could also say that this is the case such that we can now multiply by our k value or get intervals and start getting coterminals. We're going to see that in just a minute. Let's take a look at one now, in fact. Let's say that we are trying to find all of the solutions for the sine of theta equals 1/2. Well, the sine of theta is going to equal 1/2 at pi over 2 in the first quadrant, pi over 6 in the first quadrant, and 5 pi over 6 in the second quadrant. Now, these two answers are only on the interval from 0 pi to 2 pi. Notice it doesn't include 2 pi. But if I want all of my solutions, I'm looking at pi over 6 plus 2 pi k, such that k is an element of the integer set. We would then do the same thing with 5 pi over 6. We are creating a sequence of values. And we have 5 pi over 6 plus 2 pi k, such that k is an element of the integer set. These are now my solutions for theta. These are the solutions if I have a restricted domain, and these are the solutions if my domain is infinite. In other words, we can keep going around the circle, or we're looking at a graph that oscillates infinitely. Now, if you think about a graph that oscillates infinitely, it becomes readily apparent that there are going to be an infinite number of solutions. Why? Well, stop and think about what it is you've graphed. It's sinusoidal, it is periodic, and if I'm looking at 1 here, then 1/2 is here. Notice how many times it cuts through each of these curves over and over and over again. This first one is pi over 6. This one is pi over 6 plus 2 pi. This one is 5 pi over 6. And this one right here is 5 pi over 6 plus 2 pi. This one all the way over here is pi over 6, and it is adding to it not just 1 period, but 2. That's 4 pi. So we can clearly see that pi over 6 plus 2 pi, pi over 6 plus 4 pi, which means that there's going to be another solution called pi over 6 plus 6 pi, pi over 6 plus 8 pi, pi over 6 plus 10 pi. And you're never going to be able to write them all down. So you have to write it as a sequence. Okay? Once again, solutions. How do we find our solutions? How do we solve for our polynomials? Alrighty, this is part 1 of verifying identities. And then in our next video, we're going to be talking about solving our polynomials so that we can find all of the polynomial solutions, and these are trigonometric polynomials, or polynomials within a restricted domain. Alrighty, thank you very much. I appreciate you paying attention, and please let me know if this was helpful. Bye-bye now. Be well and take care.